Okay, guys, I'm going to take up the homework from the last couple of days. So in 12.1, you learned about dispersion. So there are three different types of dispersion. So this was one of the questions I asked you on LMS. What are the three types of dispersion? It's as simple as clumped, okay? And they show you a school of fish. Random, like trees that'll spread out randomly. And uniform, where things are like perfectly placed, okay? So those are your three types of dispersion. What else did I ask you there? Sampling methods. Okay, so really super quickly here. There are two types of sampling methods. There are actually three, but we're going to go with the two that you've read about here, and they're the most common. So you could use a quadrat. A quadrat is literally this, okay? It's a square that a biologist will throw down and count the number of organisms or individuals that they find within that square. So what we're doing here is trying to estimate population size. And why would you want to do that? Especially in 2020, it's because we've got climate change. We want to know if organisms are endangered or on the verge of extinction, all of those things, or if they're thriving, or if they're taking over a certain area, right? All of these things matter all the time. So this is a quadrat. It's basically four rulers stuck together. You throw it down randomly. You can't choose where you throw it. You just throw it randomly and you sample and then you count how many individuals are in there, okay? This works really well for plants because plants aren't moving, and it would work well for very slow moving organisms like a snail, okay? You can count the number of snails in a certain area by throwing that down. What this is not going to work for is anything that's moving quickly, okay? So what people do then for animals that are moving quickly, and you want to, for example, study the bald-headed eagle population because they were so in so much danger years ago, they would do mark recapture or capture recapture, okay? It's called either of those. And so what you do is you collect a whole bunch of animals, as many as you can find, and you mark them, okay? Now, there are some things that we have to assume that are happening, 5 assumptions, okay? So these 5 assumptions are important. Normally, I'd really emphasize them. What are 5 things that we have to assume when we capture these animals? And I would normally try and get that from you guys before telling you. And so they're right here, okay? So basically you have to make sure that you're not marking them with a bright pink tag, because if you give them a bright pink tag, the predators are going to find them and their prey is going to see them coming. Okay, the thing that's attached to them, the marker, cannot injure them in any way, or like you can't be afraid it's going to get snagged on something. Okay, so that's number 4 here. Basically, the captured animals are not adversely affected by their markers. Okay, the marked animals do not lose their markers. So you have to make sure that this marker or tracer is something that's going to stay with them. Okay, and then there are a few others here that you can read through. And then, so what we're doing is this: we're capturing individuals and marking them. Okay, and then we're releasing them again. And then let's say 6 months later or a year later would be a great time to do it. So we could look at breeding seasons every single year. And so when the animals come back to breed, so let's say robins, so we mark a certain number of robins. And then what we want to know is if the city lights are bothering them, if they're hitting the walls and they're hitting skyscrapers, okay, and how many we're losing. So then when they come back a year later, we capture as many as we can in that same environment, and we count how many have been marked. So how many of those guys still have markers on them? And then we count how many we've captured altogether. So let's say that we originally capture 50 and mark 50 in 2019, and then in 2020 we are able to capture 40. Okay, and then we look at how many of those 40 little m have markers on them. And from that, there are a lot of assumptions to be made, these 5 assumptions. We can estimate our population size. It is pretty good a method, all right? It's not perfect, but it's a pretty good method if you're going back at a proper interval and your tags are not causing those animals any harm. And then capital N is what we're always trying to find, and that's the total population size, okay? So those are the 2 methods that we looked at. And so taking up these questions, do dispersion patterns of populations always stay the same? Obviously not, okay? Obviously, depending on the environment and seasons and etc., dispersion patterns aren't set in stone. Okay, and then I answered those 2 questions for you. So 3 ways that dispersion occurs, and sampling methods I've gone over with you. And then question number 5, okay, I have that over here. So if we look at those numbers, okay, I don't know why I did 6 before 5, but I did. Here are your answers. Trying to find the population. These are our individuals we marked initially. These are the number of individuals that returned to us, and these are the number of individuals that were marked that returned to us. And so these are your numbers, okay? And this is your answer. And then for question number 6, we're trying to find population density with a quadrat sampling. And so we throw out 5 quadrats, and each time we throw out a quadrat, I can't remember what the population is. Oh, dandelions, right, it's right there. Okay, so we find 6, 10, etc. dandelions. We've sent out 5 1 meter squared quadrats. So in other words, the box was 1 meter by 1 meter. Okay, and so that's when we did it 5 times. So that's where this number comes from. And we get 5.8 dandelions per meter square. So basically we're taking an average here, all right? And then if we want to find that's our population density for that area. If we want to estimate our population size, then we take the 5.9 dandelions and we say, okay, what was the total area that we were sampling? And we threw down 5 random samples, but what was our area? And they told us it was 40 meters by 40 meters. And so I've done the long math here for you. You certainly don't need to make it this long, but just in case some of you guys struggle with math, I thought I'd lay it out for you. So we've got 5.8 dandelions, and then this equals 16 meters squared. Cross out your units if one's above a division sign and one's below, and your estimate is 9,280 dandelions for that 1,600 meters squared. All right, so that's one set of answers. The next thing I didn't take up with you is on page 499, or 599. So I'm going to take these up. Sorry, I'm talking a mile a minute because I don't want to waste your time. List 4 factors that change the number of individuals in a population and describe how each factor affects the population. So here we're just talking about births, immigration, deaths, and emigration. Births and immigration contribute positively to your population, and deaths and emigration contribute negatively. Okay, number 4, choose an organism that has each type of survivorship curve. Explain why it has this type of curve. So you had to do a little bit of research. I'm not going to give you the answers there, but you had to find type 1, type 2, type 3. All right? Use table 1 on page 593 to answer these questions. So if we go back to 593, sorry, I'm going to make you a little dizzy here. At which age interval is the population reproducing at its highest rate? So we have to look at reproductive rate. Okay, sorry, dying, this is alive, dying, age-specific mortality, survivorship, original cohort at live. So if we're looking at reproductive rate, okay, is that what it's asking us? Reproducing at its highest rate. So I would say, looking over here, reproducing at its highest rate would be right here, okay, looking at its survivorship rate. Now, I think I might have made a mistake on that because I'm just doing this on the fly here. So age-specific survivorship, yeah, no, that sounds good, okay? So reproducing at its highest rate would be at the beginning. And then at what age interval is mortality at its highest? So we just have to look at mortality, and we're going to come to mortality rate is at its highest down here, okay? So this doesn't sound like it doesn't seem like I'm coinciding with the lesson I taught you earlier. Survivorship rate, cohorts alive, yeah. Oh, fecundity. So age-specific fecundity, the age-specific fecundity was highest here. So for question 6A, this is when it had its highest fecundity. So we're going to say that's when it was reproducing the best, okay? Clearly there are more individuals alive to reproduce here, but if we look at fecundity, that's what I'm going to go with, okay? And then B says, at which age interval is the mortality rate the highest? So our mortality rate is the highest between 7 and 9, okay? 7 and 9 years after the plants were made. What is the probability of a member of the cohort being alive in the 13 to 15 month range? So, oh, these were months. Sorry, I thought these were years. Okay, so the lesson before I said years. So these are months. And what is the probability of an organism still being alive? It's 38%. All right, we're looking at this age-specific survivorship. So it's about 38%. And then based on the information in Table 1, what type of survivorship curve would best reflect this? I would say definitely a type 2, okay? Because our numbers are going down steadily. We're not seeing a high survivorship at the beginning or a high survivorship at the end. And this is a plant, so it stands to reason most plants have a type 2 survivorship curve. All right. And then number 7, list and describe 3 factors that could affect the fecundity of a population. So you will have those 3 factors. I will be very honest with you, I didn't look them up. Okay, so we're going to look at environmental conditions, okay, age structure, and then I would say parental care. Okay, so we definitely know that fecundity is dependent on environmental conditions. Okay, environmental or age structure. So how long are you going to live? There's only so much. If you're only going to live 2 years, your fecundity is going to be very different than if you're going to live for like 75 years. Okay, and so your sexual maturity, your reproducing age, they're giving them to us there. All right, and number 8. Over a population. Okay, so this is our mouse population, and I did this one for you as well. All right, and that would be right here. Okay, so our change in population, all right, delta N would equal our births and our immigration, subtract our deaths, and there was no emigration, and so we get a population change of 360, and that's positive, so we have a growing population.